Hello friends, I welcome you all for this video lecture on VLSI design. So in this unit, we are going to see the CMOS clocking and the VLSI system design using the Verilog LGL. Now let's see a modules. So Verilog provides a concept of a module. So module is nothing but the basic building block in the Verilog. Suppose if you are designing an adder circuit, then we will give a name to the module as adder. A module can be an element or a collection of lower level design blocks. Typically, the elements are grouped into the modules to provide a common functionality that is used at many places in the design. A module provides the necessary functionality to the higher level blocks through its port interface, that is input and outputs, but it hides the internal implementation of the circuit. So this will allow the designer to modify the module internals without affecting the rest of the design. Okay, so this module is nothing but a basic building block. Okay, so that only contains the input and outputs. Now let's see the components of the Verilog module. A module definition is always begin with a keyword, that is module. So module name, then port list, then port declaration, and optional parameter must come first in the module definition. Okay, so let's see the components, which are the different components in the Verilog modules. So module is always begin with a keyword, that is module, then next is the module name. Okay, suppose if you are designing an adder circuit, then the module name is adder. Okay, then next is a port list. Okay, means to this particular building blocks, what are the inputs terminals and output terminals, so that list. Okay, so in that, when we are specifying the port list, we first write the output terminals and then the input terminals, that is called as the port list. Then port declaration, if the ports are present. Okay, so if we going to write the inputs and output ports. Okay, so here in the port declaration we are defining that particular port as an output or input or in out. So there are the three keywords for that, for specifying the port as input. So for that there is a keyword, that is input. Similarly, for the output we are having the keyword output, and if both bidirectional terminals are there, then we are using the in out keywords. Then the parameters that are optional. If the parameters are different parameters are present within the module, we can write that particular parameter. Now in the body of that particular module, now this is the declaration. Okay, this is the module declaration. Okay, so module declaration will start with the keyword module, then module name, then port list, then the declaration of the ports. Okay, now after that we have to declare the wires or the resistors. Okay, so declaration of the wires and the resistor and other variables. Okay, so if you are defining any particular terminal as a wire, okay, so this will hold the current, this will hold only the current values of that particular variable. Okay, and if you are going to declare it is as the resistor. Okay, so for that keyword is reg, that is the resistor, and to defining the terminal as a wire, the keyword is wire. Okay, so if you are defining the input or output as a resistor, then it will hold all the values of that particular variable. Okay, during the simulation time, all the simulation time. Okay, but the difference is between the wires and the resistor is only that, okay, wire will hold the values only for the current simulation time. Okay, but the resistor will hold all the values of the variables. Then next to that is the data flow statement. Okay, So we will see in detail what is how we are going to write data flow modeling of the Verilog circuit or the VLSI circuit. So a data flow statement will always begin with assign keywords. Okay, so assign is a keyword. So if the assign keywords will be there, means that is the data flow assign statement. Then next, the instantiation of the lower level modules. Okay, so we can instantiate the lower level modules so many number of times. Okay, depending upon the requirement. Then always an initial blocks. So always an initial block will becomes in the behavioral modeling. Okay, so all the behavioral statement goes with this particular block. And last, the task and function. Okay, so there are the we are already seeing some system tasks. Okay, and a function. Okay, so we can use this system tasks and function. Okay, so these are the main 5 parts of this modules. Okay, then at last we have to end module. Okay, so the end module statement comes. Okay, so that will tells this module particular whatever the module we have defined, that module will be end. So let's see, the port list and the port declarations are present only if the module has its any ports to interact with the external environment. The 5 components within the modules are the variable declaration, the data flow statement, then instantiation of the lower level modules, the behavioral block, and system task or the function. So this component can be in any order and at any particular place in the module definition. And the end module statement must always come last in the module definition. All the components except module, module name, and end modules are optional and can be mixed and matched as per the design needs or the design requirements. The Verilog allows the multiple modules to be defined in a single file, and the modules can be defined in any order in that particular file. Now let's see an example for the component of SR latch. Okay, so we have already seen how to specify the comment. Okay, so the single line comment will be specified with the double slash. Okay, double slash. This example illustrates the different components of a module. Okay, so this is the comment. Then double slash module name and port list. Double slash SR latch module. Okay, so we are going to write the module for the SR latch. Okay, so here on this particular left hand side we can see the SR latch. Okay, so so for this SR latch we are having the 2 inputs and 2 outputs. So what are the inputs? That is S bar, that is set, and the R bar, that is reset. And what are the output? Q and Q bar. If you have seen the internal implementation of this SR latch, so it is having 2 NAND gates. Okay, that is N1 and N2. Okay, so that is the internal implementation. So let's see how we can write a module for the SR latch. So module, okay, so module is the keyword, then SR underscore latch. Okay, so SR underscore latch is the module name. Then in bracket we are going to specify here the port list. Okay, so when we are writing the port list, we write the output port first and then the input ports. So output ports are the Q and Q bar. So Q comma Q bar, then S bar comma R bar. Okay, parenthesis bracket complete semicolon. So this is the way to write a module. Okay, so module SR underscore latch in bracket Q comma Q bar comma S bar comma R bar bracket complete semicolon. Now next double slash port declaration. Okay, so this is the comment. So we have to define the port list now. Okay, so for that there are the 3 keywords to define the port list in the Verilog, that is input, output, and inout. Okay, so output Q comma Q bar semicolon. So Q and Q bar are the outputs. Then input S bar comma R bar semicolon. So here we have defined the S bar and R bar as the input. Now double slash instantiate the lower level modules. Okay, so this is a comment. Then in this case the instantiation in this case the instantiate the Verilog primitive NAND gates. Okay, note how the wires are connected in a cross coupled fashion. Okay, so so there are the six gate primitives are provided in the Verilog. Okay, so here as we have seen the internal circuit of this SR latch, so there are the two NAND gates. Okay, and to specify this in the Verilog, we use the gate primitive, that is NAND. Okay, then n1 is nothing but the instantiation name. Okay, n1 is nothing but the instantiation of the NAND gate. So NAND n1, then port list. Okay, so in bracket q comma s bar comma q bar, bracket complete, semicolon. So this is the declaration of the first port. Then second, NAND n2 is the instantiation of the NAND gate, then q bar comma r bar comma q, bracket complete, semicolon. Okay, and after that we have to end module. So we are using the keyword, that is end module. Okay, now so here earlier we have write the that module definition of this SR latch. Now after after we have designed this SR latch, we have to simulate this particular SR latch so that we can verify whatever we have designed that is correct or not. So for that we have to write the stimulus module. Okay, so now let's see how to write the stimulus module. Module top semicolon. Okay, so here module is the keyword, then top is the module name, then wire q comma q bar semicolon. Okay, so we have defined the output as wire. So meaning is that the q and q bar values will not be stored for all the simulation time. It only shows for a current simulation time. Then register set or reset. Okay, so when we are specifying it is as reg, that is register. Okay, reg is a keyword. So when we are specifying this is as a register, so the set and reset values will be stored for all the simulation time. Okay, then initial means the simulation will be started. Okay, so initial is nothing but a behavioral statement. Then begin means simulation started. Then $monitor is a system task. Okay, so that is used to monitor a particular variable. Okay, so $monitor in bracket $time means current simulation time. Okay, comma double quote set equals to %b. Okay, so we are defining the set variable as binary. Then comma reset equals to %b means reset variable as binary. Then q equals to binary %b. Okay, slash n. Then comma set comma reset comma q. Now next, set equals to 0, so we have assigned the 0 to the set. Then reset equals to 0, we have assigned the reset as equals to 0. Now hash 5 means after the 5 simulation time, after the 5 clock pulses, the reset will become equals to 1. Okay, again next hash 5 reset equals to 0. Again after the 5 clock cycle means after the 10 clock cycle, reset will be equals to 0. Then hash 5 means after the 15 clock cycle, set becomes equals to 1. Then end. Okay, and end module. Okay, so here whenever we have use the keyword begin, we have to end it. Okay, and if you are writing the module will be end with the end module. Okay. Now let's see the ports and the list of ports. Okay, so here you can see at this bottom we have defined this particular module, that is top, that okay, that containing the full adder, that is 4 bit. Okay, so here that module name is given as full add 4. Okay, what are the ports are there? A, B, then C underscore in, that is input, and what is the output? That is sum and C out, C underscore out, that are the output. So that is nothing but a port list. Now the ports provide the interface by which a module can communicate with its environment. Okay, so for example, input or output pins of an IC chips are its port. Okay, so as we have seen in this particular figure of the full adder, that is 4-bit full adder. So environment can interact with the module only through its ports. Okay, so we are going to define a module. Okay, and uh, uh, we will communicate this particular signal with the help of its port list. The internal of the module are not visible to the environment. Okay, we are just because we have already seen the module is nothing but the basic building block of the uh, design. This provides a very powerful flexibility to the designer, because we have just designed a top level module. Okay, we have not implemented the internal implementation. Okay, so whenever the designer has to change the internal implementation, okay, so it is easier, or it will provide a flexibility to designer. The internals of the module can be changed without affecting the environment, as long as the interface is not modified. The ports are also referenced as terminals. Now let's see the port list. A module definition contains the optional list of ports. If the module does not exchange any signal with environment, there is no port in the list. So consider a 4-bit adder that is instantiated inside a top level module top. So here how we can specify this list of ports. Now let's see module, that is the keyword, then full add 4, that is the module name, and in brackets sum comma C underscore out comma A comma B comma C underscore in, bracket complete, semicolon. Okay, so module is a keyword, then full add 4 is the module name, then in this particular parenthesis bracket, this is nothing but a port list. Okay, so port list is nothing but the number of terminals to the basic building blocks. Then module top. Okay, now how to write the port declaration? So all the port in the list of port must be declared in the module. The port can be declared as follows. So module full add 4 in bracket sum comma C underscore out comma A comma B comma C underscore in, bracket complete, semicolon. Now let's see how this port declaration will be done. Okay, so you can see this particular table, okay, at the bottom, that is Verilog keyword input, that is used for the input port declaration, then output for output port declaration, and in out for the bidirectional port. Okay, so output that is in square bracket 3:0 sum. Okay, so here we have defined the vector sum, that is vector variable sum, so means sum will having the 4 bits. Okay, then output C underscore out, input in square bracket 3:0 A comma B, means both A and B are of the 4-bit size, then input C underscore in. So likewise we can define the port list. Then after that we can define, or we can declare the module that internal circuits of the module, and then end module. Now let's see the port example of the port declaration for the D flip-flop. So module is the keyword, then dff is the module name, then in bracket q comma d comma clk comma reset bracket complete semicolon. Okay, so this is the port list. Now output q. Okay, the output of this D flip-flop is Q. Then REG, that is the register Q. So we are defining this output variable as a register, means it will hold the values of this variable for all the simulation time. Then input D comma CLK comma reset semicolon. So these are the inputs. Then end module. Now let's see the port connection rules. Okay, so you can see this figure in this particular. So here in that particular slide, it is defined how to declare the ports. Okay, so here at the left side you can see the register or net. Okay, outside this particular model block, and if you are defining it is at the internal of this particular model, then it is defined as input net. Okay, input will be defined as net. Then similarly at the right side, okay, you can see it is defined as net. Okay, and the output internal to the model will be defined as register or net. Okay, and if there are the bidirectional bus, then we use in-out keywords. Okay, and here both outside this model block as well as internal to the model block, we are defining this as net. Okay, so remember this. Okay, so we can define it is as net or register. Okay, input and output. Okay, but you can remember this, we can define it is a register or net outside the model block for the input. Okay, and for the output we can use this register or net internal of that particular model. Okay, then output as net for the output, and for the input we can define it is as net internally. Okay, so one can visualize a port as consisting of two units, one unit that is internal to the model and another that is external to the model. So internal and external units are connected, and there are the rules governing the port connections when a model is instantiated within the other modules. Okay. So let's see the port connection rules. Inputs. So internally the input ports must always be the type net. Externally the input can be connected to the variable which is a register or a net. Then output. Internally the output port can be of the type register or net, but externally the output must be always connected to a net, and they cannot be connected to a register. Then in-out. Internally the in-out ports must always be a type of net, and externally in-out port must always be connected to a net. Then width matching. So it is illegal to connect the internal and external items of different size when making the inter-module port connections. However, a warning is typically issued that the widths do not match. Then unconnected ports. The Verilog allows the port to remain unconnected. For example, the certain output ports might be simply for the debugging, and you might not be interested in the connecting them to the external signal. Now let's see an example of this, that is full add 4, that is the module name, then FA0. Okay, so that is the instantiation of this full add 4. Then in brackets sum comma, that is C out comma A comma B comma C underscore in. So here in this particular case we have not written the C underscore out. Okay, so that is the unconnected ports. Okay, so we can write in the Verilog as this, that is in bracket sum, then comma A comma B comma C underscore in. Then connecting ports to the external signal. So there are the two methods for making the connection between the signal specified in the module instantiation and the ports in a module definition. So connecting band order list. So what is that? Connecting band order list is the most uh, intuitive method for the that is most beginner. The signals to be connected must appear in the module instantiation in the same order as the ports in the port list of module definition. Okay, so for example, module full add 4 in bracket sum comma c underscore out comma a comma b comma c underscore in bracket complete semicolon. Then here when we are defining this, so we will follow the how we have or how we have defined this port list. So in the same order we are going to declare this port list. Output in square bracket 3:0 sum, then output c underscore c out c underscore out, then input in square bracket 3:0 a comma b, and input c underscore in. Okay, so this is the way where we are connecting band order list. Okay, so whatever the port list we are defined in the same order we are defining this port declaration. Then end module. Okay, so the module internal, then end module. Then next, how to write this stimulus module for that. So module top register 3:0 a comma b, register c underscore in, then wire in square bracket 3:0 sum wire 3 underscore out. Okay, then full add 4 fa underscore ordered sum comma c underscore out comma a comma b comma c underscore in, then stimulus, then end module. Now another, we can declare or we can connect the port by its name. Okay, so for the large design where the module have say the 50 ports, so remembering the order of the ports in the module definition is impractical and error prone, because if there are the numbers of ports, so we cannot remember all the ports. Okay, so in that particular case we can use the port name. So Verilog provides the capability to connect the external signal to the port by the port names rather than its position. So example of this is full add 4, then fa underscore by name is a instantiation, then in bracket dot c underscore out in bracket c underscore out comma dot sum in bracket sum comma dot b in bracket b dot c underscore in bracket c underscore in, then dot a in bracket a. Okay, then bracket complete semicolon. Then full add 4 fa underscore by name in bracket dot sum in bracket sum comma dot b in bracket b, then dot c underscore in bracket c underscore in comma dot a in bracket a, bracket complete semicolon. Then next is a hierarchical name. So every module instantiates or every module instance or the signal or variable is defined with an identifier. A particular identifier has a unique place in a design hierarchy. So hierarchy name is names referencing allows us to denote every identifier in the design hierarchy with a unique name. So an hierarchy name is the list of identifiers separated by a dots for each level of hierarchy. So you can see this hierarchy, that is stimulus, then stimulus dot q bar, then stimulus dot reset, stimulus dot m1 dot q1, then stimulus dot m1 dot s, then stimulus n1. Okay, so here you can see that figure, stimulus, that is root level. Okay, then m1 SR latch, then n1 NAND gate, then n2 NAND gate, and their port list are q bar, s, comma, r, that are the signals, and here the variables are q bar, set and reset. So those are the variables. Now let's see an important topic, that is propagation delay. Okay, so you already know what is the propagation delay. Okay, so propagation delay is nothing but the time required for any circuit to convey the input okay, at output. Okay, so in a VHDL there are the two types of the delay that can be used for modeling behavior. So first is the inertial delay, so it is most commonly used, and while the transport delay is used where the wire delay model is required. So let's see what is the inertial delay. So inertial delay is the default in a VHDL, and if no delay type is specified, the inertial delay is used. Inertial delay is a default because in the most cases it behaves similar to the actual devices. Okay. So in an inertial delay model, the output signal of the device has inertia, so which must overcome for the signal to change its value. The inertia value is equal to the delay through the device. Okay, so delay means after the application of the input, at what particular time we get the output. So that is the delay. If there are any spikes, pulses, and so on that have the period where a signal value is maintained for less than a delay through the device, the output signal value does not change. Okay, and if the signal value is maintained at a particular value for longer than the delay through the device, the inertia is overcome and the device changes to its new state. Okay, so this is the inertial delay. Okay, so if the spikes or the pulses will having the less as compared to the delay of the device, then output will not change, and if the signal values are maintained at a particular values for the longer than the delay, then the output will changes. One more reason for the widespread use of the inertial delay is that it prevents the prolific propagation of the spike through the circuits. Now let's see this buffer that is having input A and output B, and the delay of the buffer is 20 milliseconds. Okay, so whenever we are applying the input, that is A, so if this input is having the spikes less than the delay of that particular circuit, then the output will not change, and if this delay if the input is greater than this particular delay of that particular device, then it will change its output. So the figure is an example of very simple buffer symbol. The buffer has a single input A and a single output B. The waveforms are shown for the input A and output B. A change from 0 to 1 at 10 nanosecond and from 1 to 0 at 20 nanosecond. So this creates a pulse or the spike that is of a 10 nanosecond in the duration, and the buffer has a 20 nanosecond delay through the device. Okay, so this spike is less than the device delay. Okay, so that's why it does not change the output. Okay, So the 0 to 1 transition on the signal causes the buffer model to be executed and scheduled at event with the value 1 to occur an output B at particular time 30 nanosecond. Okay, so spikes will come at 10 nanoseconds. So adding a delay to that, so we will get any particular changes after the 30 nanosecond. But at a 20 nanosecond, the next event on the signal A is occurred, and this execute the buffer model again, and the buffer model predicts the new event on the output B of a 0 value at a time 40 nanosecond. So the event on output B for 30 nanosecond still not occurred, and the new event predicts by the buffer model clashes with the currently scheduled event, and simulator preempt the event at 30 nanosecond. The effect of this preemption is that the spike is swallowed. The reason for the cancellation is that according to the initial delay model, the first event at 30 nanosecond did not have enough time to overcome the inertia of the output signal. Okay, so next we can see the transport delay. A transport delay is not default in the VHDL and it must be specified. Okay, so if it is not specified, then it is a transport delay. It represents wire delay in which any pulses is propagated through the output signal delayed by a delay value specified. The transport delay is especially useful for modeling a delay line devices, the wire delay on a PC board, or the part delay in an ASICs. Okay, that is application specific integrated circuit. So we are having the same buffer that is having the delay 20 nanosecond. Now let's see the input. So input A will changes its state from 0 to 1 at 10 nanosecond. Okay, so means this will appear at the output B at 30 nanosecond, means 10 plus 20 delay, 20 nanosecond delay, that is 30 nanosecond. Okay, and after that the A input will be changes its state from 1 to 0. Okay, so this will propagate at output. Okay, after adding a delay. Okay, so 20 nanosecond plus 20 nanosecond is 40 nanosecond. Okay, so you can see the same 10 nanosecond spike. Okay, you can see this 10 nanosecond spike in input A will be transferred or transported to the output B. Okay, so this is the difference between the inertial delay on the transport delay. At a time 10 nanosecond, the buffer model is executed and they schedule an event for an output to go to one value at 30 nanosecond. At 20 nanosecond, the buffer model is revoked and predicts a new value for the output at 40 nanosecond. So with the transport delay algorithm, the events are put in order, and the events for the time 40 nanosecond is put in the list of the event after the event for the time 30 nanosecond. The spikes is not swallowed but is propagated intact after the delayed time of the devices. Now let's see how to specify the delay in a level modeling. Delays are shown by hash in all the log modeling levels. Okay, so if the hash will becomes as the first character, then it is a delay. The inertia rise delay, inertia falls delay, then inertia turn off delay. Okay, so for example, and hash in bracket rise underscore value means rise value, then false underscore value means false value, comma turn off underscore value means turn off value, bracket complete. A is the instantiation of the AND gate, then out comma in 1 comma in 2, so that is the port list for the AND gate. So this is the way we are going to specify the delay, gate level delay. So thank you for watching this video lecture. So please like, subscribe and press a bell icon so that you can receive the alert for the next upcoming videos. Thank you. Thank you all.